Okay, welcome back. Let's try and finish these slides if we can. Let's do our best. So let's start getting into recursion now. This slide, the set of slides is called induction and recursion. Let's actually get into more recursion. So the first thing that I want to talk about is recursive definitions. You can define things recursively, and we're going to notice that recursion and induction kind of look the same. So let's start with this. So let's define a set of balanced parentheses. Like here are some balanced parentheses, like in a programming language. Just they always are balanced. They never end abruptly without closing one off. Things like that. That's what it means to be balanced. And you can define this with recursive rules. You can have a base case, kind of, which is called a basis in your book. And that's saying that in the set of all the strings of balanced parentheses, you can start it off with the empty string. No parentheses at all. They're by default balanced, right? An empty string is totally balanced. So nothing at all has balanced parentheses. That's fine. And then you can fill in the rest with recursive rules, where you take stuff out of the existing set and you put new stuff in, which is kind of cool. So for example, if something is in balance, in bal the set, then put that thing surrounded by parentheses in balanced too, because it will also be balanced. Interesting, huh? So that's how you can build stuff up from existing stuff. So for example, from the empty string, concatenate it with parentheses on both sides, that makes this string, which holds balanced parentheses. You could use that with the same rule and surround it with parentheses, and it again makes a string of balanced parentheses. Isn't that neat? So that's one recursive rule. And then here's the other. If you have two strings of balanced parentheses, then you can concatenate those, and they are still balanced. So for example, if we take this one and concatenate it with this one, in either direction, honestly, you end up with boop boop and boop 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 boop. That is another string of balanced parentheses. Do you see how we're building things up based on existing stuff? And so this is, of course, an infinite set. There are plenty more things that you can use, but there are only a finite number of rules to fill it. Isn't that cool? So yeah, the reason we can go from the empty string to this is because anything concatenated with the empty string anywhere just takes away the empty string. That's kind of like nothingness, right? So yeah, if you use just those rules to define the set, then bal contains nothing but balanced parentheses. And I guess that's supposed to be bold. Okay, so that's a recursive definition. Let's have some more examples of those. So here is a recursive definition of a certain kind of binary strings. Okay, so strings of ones and zeros. And so let's make a set that contains only binary strings if they have this property. Okay, the set S consists of all strings that have the same number of zeros and ones. Okay, so we're going to build up a set called S of a bunch of strings with the same number of zeros and ones. So the empty string totally has the same number of zeros and ones, like same with 0, 1, 1, 0, dot, 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 0, 1, 0, 1. It all works out, right? So how can we fill in and make this set? Okay, so again, we can have a basis. The very first thing that we can put in this set is we can define it holding the empty string first. That's always having the same number of zeros and ones, particularly 0 zeros and 0 ones. And then here are our recursive rules that help build this special set. So if x is in S, add the following. You can either do this or this. So add both 0x1, right? So put the same number of zeros and the same number of ones with the 0 on the left. So add that one to the set, and also add 1x0 to the set with the 1 on the left and the 0 on the right. So that's one rule. And then the other one is if x and y are both in S, add their concatenation, xy, to that set again. Okay, and this will build up all the strings that have the same number of zeros and ones, because it will all work out. Okay, so this concatenation also works. These both individually had the same number of zeros and ones, and so together they will as well. Okay, so for example, that's how we could build these. So we could use this rule plus lambda to get this string. We could use this rule plus lambda to get this string. We just keep adding it into S. Okay, Then finally we could use this string with itself to get this string, using the concatenation rule, and they always have the same number of zeros and ones. Isn't that neat? And so if you pick the right rules, you can build a set with just the elements of that respect some property. That's quite nice. And then you can go and prove that they have that property as well. Like these were the correct rules to add. So that's the thing. So those are recursive definitions. I hope they make a bit of sense, because that's leading us into recursive algorithms, right? If you have a recursive algorithm, that means it's calling itself. It's using its own results to build up answers to bigger problems. It calls itself on smaller input values. That's the key, right? When you have a recursive function, it better call itself only on smaller values for some sense of the word smaller. Otherwise, it will never end, and we'll get infinite recursion, which we do not like, right? So yeah, when you call yourself, it's called a recursive call, and when you're proving that a recursive algorithm works, you get to essentially assume, right? You assume that the smaller recursive call does the right thing, and as long as you build up the right answer, the whole thing will be correct. So that's very similar to induction, wink wink. We'll get into that. And let's remember like the classic example of how to calculate the factorials of a number. So the base case would be calculating 0 factorial, that's defined to be 1, just immediately return 1. And then the recursive case is noticing that if you want to calculate n factorial, that's just n times n minus 1 factorial. And let me show you why this works. So for example, here's how we notice those rules, like 0 factorial, it is defined to be just 1. And then like 5 factorial, it's 5 times 4 times 3 times 2 times 1, right, for 0 factorial. And this is equal to 4 factorial. So let me show you the recursion tree so we can see why 5 factorial using these rules is going to work. So 5 factorial goes off and it computes, well, it's just 5 times 4 factorial, a smaller recursive call to the factorial function, which is going to go off and compute 4 times 3 factorial first to then run this rule and multiply it by its 5. And then 3 factorial, what's that but 3 times 2 factorial? Well, it's 2 factorial, but 2 times 1 factorial. Oops, that's supposed to be a 1. Let me do that better. There. And what's 1 factorial but 1 times 0 factorial? And 0 factorial we have defined to just be 1. And that stops our recursion. And this is like unfolding on the stack, like these are a bunch of function calls waiting to be returned, and finally it gets returned. So this returns 1 to whoever called it, like I know the answer, I can multiply that answer by 1. So the final answer for that is 1 again. And then this was waiting for 1 factorial to finish. It can multiply it by 2 to give back 2 factorial's answer. And so, man, that's 2. And so this is waiting for the 2 to multiply it by its 3 to compute 3 factorial. So that's a 6 that it returns. That was waiting for the 3 factorial to return it times 4, and that returns 24. And that was, this guy was waiting for 4 factorial to multiply it by 5. We just got that answer back, so 24 times 5 is apparently 120, because that's what 5 factorial is, okay? And that's how the recursion unfolds and unwinds and actually does the right thing. You see that? Eventually we get down to the base case, and that's when we wind back up to give back the final answer. Okay, so that's recursive algorithms in a nutshell. Hopefully they're coming back to us. And what I'd like you to do is think about how to find this. Come up with a recursive algorithm, take a little bit, to find a recursive algorithm that has the following input. The input is a sequence of numbers, just a bunch of them, like a vector maybe. You can think of it that way. And you need to return the minimum number in the sequence. You are not allowed to use a loop. You have to use recursion to do that looping process, okay? So you're given a sequence of numbers. Maybe think of it as a list. That would be easiest. And then you perform a recursive process on that thing, okay? So here's the idea. Let's say that we're given as input a list L. Did you get it? So maybe like our list is using racket syntax 8675 309, and we're looking for the minimum. Usually what you do when you recurse on a sequence is you like split it into the first thing and the rest of the list, okay? That's essentially what you do. So usually you recurse, that's the verb form. you recurse on the length of the sequence. That's the thing that gets smaller across recursive calls. You make a recursive call to a smaller sequence. And so you can split up any list, any sequence that you're given, into a first element and the rest of the list. Okay? That's the goal. And so what you're going to do is like find a base case, find a recursive case. Let's talk about like the base case, right? The minimum element in any number, in any sequence with just one thing in it is that number, right? A list with just n in it, the minimum element is just n. So the base case is when you have a size 1 list. Size of L is 1. Just return that element. You found the minimum. Okay? The recursive case involves making a recursive call on the smaller list. Recursive case. What you do is you recursively find the min of the rest, the smaller sequence, okay? And you're going to get back an answer. You assume that it does the right thing and finds the correct minimum of that sequence, that subsequence, and then you compare it with the first element, the one that you haven't looked at yet, okay? So that's the first element, it's 8. The recursive call on rest will get back the minimum of this subsequence, which is 0. You compare that with 8. Compare that in each direction, and it looks like 0 wins, so the 0 was the minimum of the whole thing. And that's how you give back the answer. That's the algorithm. Okay? Is that something that you came up with? That is, that seems to be the standard way that I would think about it. Okay? That's using recursion, making a recursive call on the smaller list. That is the goal there. And so this is very similar to induction, right? We've talked about similar words when we talked about recursion and when we talked about induction. Now it's time to bring them together. You can use induction to prove that recursive algorithms are correct. Isn't that beautiful? So the idea is when you're doing induction, you always have to induct on a number, right? I'm doing induction on the number n. I'm trying to prove that some predicate is true for all n, right? You have to specify what number you're inducting on, though we don't say it anymore, right? I just kind of don't talk about the predicate anymore. It always still exists, right? There's some predicate that takes a number that we're working on, where that number is essentially the size of our input, for example, when we're doing recursion. It's some measure that gets smaller when we make recursive calls, okay? So that's my hint to you. If you're going to prove that a recursive algorithm is correct, you always do induction on the thing that gets smaller across recursive calls, okay? And that might just be a lot of words. Let me prove to you that this makes sense and works for factorial, okay? So here's my factorial function just in pseudocode. That's exactly what we were talking about. And that will be hopefully a good first proof combining induction and recursion. Okay, so the number, the thing that's getting smaller when we do the recursive call to factorial is that input, is the number itself. We're calculating a smaller factorial. Okay, so what we're going to do is we're going to prove that factorial works by induction on the parameter, on that input parameter n. Okay, so we always say what we're inducting on. What's the thing that's getting smaller? Proof. And usually you say like by induction on n, okay? And then we have a base case and a recursive case now. So what are we trying to do? Factorial correctly computes the factorial. What is our predicate? Like p of n is equal to, or it's defined to be the idea that the factorial function on n is really equal to n factorial. That's what we're trying to prove, right? So the base case, smallest number that we can make this work for, that's n is 0. See that? It corresponds to the base case of the induction. Base case, of the recursion, n equal to 0. And 0 factorial is 1, and that's what's being returned. So yeah, it's correct for that case. You see that? QED there. And now the inductive step is, of course, the harder one. Here's what you do. And this is finally shedding some light on why you get to assume that the recursive call works. But it's because you're thinking about it inductively, secretly. All right? So inductive step is assume that p of k works to prove p of k plus 1. Assume that the smaller call works That's your P of K. And then prove the original call is correct. That's P of K plus 1. Okay? That's the goal. So this is when n is greater than 0, right? So that's going to get us here, right? We're always going to hit the else case of this if, or it's not going to return, right? That's essentially an else case. So what we're going to do is we're going to calculate this line. We're going to run that line, and what is R going to hold, right? We get to assume that this call works. It's a smaller call. See that? It's essentially K at that point. So get to assume that R holds, like by the IH, right? R is equal to n minus 1 factorial, for real. It did the right thing. We get to assume it did the right thing, as long as we build up the right answer. We need to show that our original P of K plus 1 call is correct. Our factorial of n call was correct. Okay, need to show we return, based on this R value, the actual n factorial. So that will prove that that call was really equal to that number. We return n factorial for that bigger number. Okay? So what we end up returning is R times n. We return R times n, which is equal to n minus 1 factorial from our inductive hypothesis, times n, which is sitting in our parameter, right? That doesn't change. And what is this but the factorial of n? Oh man. And so this is QED. We just proved that no matter the n, this factorial function, as long as it's a non-negative number, always gives back the right answer. It always really computes the actual factorial. You see that? That is a big jump. Definitely pause here, ponder this. This is a very important moment in our in this class, okay, in our computer science knowledge. We've just come full circle between induction and recursion. That is the goal of this chapter, essentially. Okay, so let's keep going while we're still hot. So here's another function. It's called reverse string. It takes a string and outputs the reverse of that string. Easy enough. So here is what it does and how it does it. For example, obviously the base case is the empty string. The reverse of the empty string is still the empty string. That's fine. The recursive case, though, is kind of interesting. It breaks it down, like say we're trying to reverse the string ABC. It breaks it down into the first element, the first character, and the rest of the characters. So remove it, and it's kind of like doing this, A and then BC. And what it's doing is it's recursively reversing that smaller string. That will make a recursive call. We get to assume it makes CB. And then we plop the A at the end of it, right? So we turn that into CBA. We plop that right there, right? CBA. And that fully reverses the string, okay? But we can prove that for any string now, because this is a for all kind of proof. One example won't cut it. Let's prove by induction that this works, okay? So what is the thing we are inducting on is the first question. What is getting smaller? What's the number? Because it's got to be a predicate involving a number, right? We're going to prove that this algorithm works by induction on the length of the input string, because that's a number that gets smaller across recursive calls, okay? Reverse string on S, where we removed a character from S, so now it's a smaller string, okay? That's the goal. So base case, again, is very easy. It works for the base case. If it's the empty string, yeah. The length of S is 0, then that means S is equal to the empty string, and the reverse of the empty string is that same string, still the empty string. Fine. Inductive step. Let's do this one. So that means S is equal to some character concatenated with, this is a symbol I'll use for concatenation, concatenated with some other smaller string, okay? That is the goal. And then, like, it's doing some work involving, like, a variable C, so let's let C be that first character, A, and then S becomes the rest, so R for the rest, all right? And then it's going to reverse it, right? By the inductive hypothesis, we get to assume that a smaller recursive call, because it's a smaller string, right? R is a smaller length than S because it has one less character in it, we get to assume that S prime really does hold that reversed string. It holds R, I guess, reversed. That's my symbol for reversed. Okay? And then we're going to calculate S. S then becomes, well, whatever it used to be, which we're assuming was R reversed, with that character C at the end of it, okay? Which was that original character A, okay? So it's R reversed with A at the end, and so it's really the very first character is now last, as it should be, and then the rest of the characters are reversed before it. And that is a correct reversed string all the time, okay? That's what it means to be reversed. Every element is in the opposite order. The next thing to the left of A was the second character in the string. Okay? So that proves that this recursive algorithm really does reverse a string. Do you see that? That's how we're doing things. So this is by the IH. By that inductive hypothesis, we get to assume that the recursive call in the smaller string does the right thing. It's a smaller number. We're using induction. That gives it to us for free, as long as we prove that the final answer is correct. We have proven the inductive step. Isn't that so cool? So this is just very fun for me. Hopefully you're also enjoying it. Here's something that I want you to try. Okay, so I went in Racket and I coded up the min list example. So we came up with that algorithm. Here's what it looks like in Racket. Use induction to prove that it really does compute the minimum of every non-empty sequence of numbers. Okay, so that is the idea. And my hint for you is that the inductive step should have two cases, because there's going to be an if statement at the end there. We have to cover all the possibilities, okay, inside of that recursive case. So, yeah, hopefully you've given that a try. Let's talk about it. So the base case is this one right here. We have a length 1 list, length 1 sequence, okay? Size of L is 1. What you do is you give back the only element in that list, the first thing, the only thing that is correct, right? Give back only the only element. And automatically that's the smallest thing. Of course, it's the only thing. So that's checked. Then we have an inductive step, which means that we only got there if the size of the list was greater than 1, right? Which means that you can break down the list into a first element concatenated with the rest of the list. Yeah? That's the goal. And then we get to assume that a recursive call on a smaller list, because we're inducting on the size of the list, right? We have those cases. We get to assume that the call to min on the smaller list, that min rest variable, will actually hold the minimum of the rest of the list. Okay, so assume by the inductive hypothesis, assume that min rest correctly holds that minimum of the rest of the list. Now we have to return the true minimum of the whole original biggest list. All right, so we have two cases, one for each part of this if statement. So case 1, that's when the first element was actually smaller than the min rest. In that case, we're going to return first, right? Because that's smaller than everything, smaller than the minimum in the rest, which means it's smaller than everything in the rest, which means it was the true minimum. So check. That's the smaller element, and we're returning it. Case 2, if min rest, if that wasn't true, we hit the else case. That means min rest is less than or equal to first, and we're returning min rest in that case. It was smaller than first, which means it's the smallest thing total. Okay, smaller or equal to it. So in every case, we're returning the smallest element, and that proves our theorem. Proves that we're actually calculating the min of the list. Okay, try this in Racket. Try coding it up. Try to unfold this and make it work. Understand why it's working. All right, so that is pretty cool. That's proving that it's really going to do the right thing. All right. So let's keep on trucking. because we now have recursive algorithms, and we've talked about complexity analysis of normal algorithms, things get a bit hairy and different when we talk about recursive algorithms and how long they take to complete. Okay, so let's talk about time complexity at a higher level. Okay, the time complexity of an algorithm, it is always like this number of steps that it takes, right, for a given input. Let's actually quantify that. Let's say that the time complexity of an algorithm is a function, t of n, that calculates the number of those basic steps, basic operations, performed by the algorithm on an input of size n. Okay? So it's always involving the input size. And so, for example, like when we have recursive algorithms, t of n is going to be defined in terms of itself, because we're asking for the time complexity of t of n minus 1 inside of t of n, right? Because we're calling it with a one smaller input a lot of the time. So we need to now somehow be able to come to terms with the fact that t of n is defined in terms of itself, like a number is defined in terms of itself somehow. We need to work with that now. So we want to analyze the complexity of a recursive algorithm and end up creating a recurrence relation. And that's what it means to have something inside of itself for the number of operations. And then we'll solve it. So we'll have like things that look like this. Like t of n is defined to be like it takes one step, and then we're also going to do some recursive work, t of n minus 1. Like we have to solve this for something, for an actual number, so we can calculate the real-time complexity. Isn't that cool? So yeah, the example that I have is what is the recurrence relation for factorial? That is, well darn, it's just exactly what I just wrote, sorry. So let me show you why that's true. Here's the recurrence relation for factorial. So how much effort does it take to solve for the factorial of a number in the inductive case? Where is that? It's, well, you're going to make the recursive call and then return after multiplying a number. So let's just assume that returning and multiplying takes one step, and then the recursive call takes, well, how much time it takes for the n minus 1th value, okay? So it's going to be make the recursive call, calculate the factorial of n minus 1, and then do some constant work after that. Some multiplication, some returning. That's just a 1 in a nutshell, okay? So that's the recurrence relation for factorial, for real, and we need a number based on this. We need an expression based on this, and I'll show you how to solve it. Okay? There are other kinds of recursive algorithms that you may have heard of before. They are called divide and conquer algorithms. So those are when you have a problem and you solve it recursively by breaking it down into subproblems, usually of the same size. So for example, here is like the idea of like merge sort. Like you're gonna take a sequence and it becomes like whatever the time it takes is split in 2 exactly. So now you have like t of n over 2, because that's the input size. T of n over 2 again, because you split it pretty much in half. Okay, that's the goal. And so that's one way to do things. Another example is binary search. That is technically not divide and conquer, but your book thinks it is, so let's just assume that it is. And remember what binary search does? It always takes what you're looking for, and it always has like a sub sequence that it's looking at. So it's looking for some value in this entire sequence. It looks in the middle because it's a sorted thing, and then based on that value, it's like, okay, the thing I was looking for must be to the left, so I'll only search in this smaller part. Again, find a middle thing. See how that compares. Oh, the thing that I was looking for can only be in the right side now because it was bigger. So I'll search over here, and eventually you're going to get down to a small enough search space where you can immediately look, and that's a very fast algorithm. Okay, so let me show you this in Racket. Let me go pull that up, and then we'll talk about it there too. Okay, to Racket we go. So here is binary search. I've also given you the min list example so that you can have that too. But here's what binary search is. You're looking through like a vector, right? A vector of things or a list of things for some value. And I've made this a 2-part series, but this is the real recursive loop. It's always you're binary searching, I call it the binary search helper, through something, some vector, between some range. Like this is the range that I'm looking through for the value. I know that if it exists, it must be there. So that's the thing I'm looking for. And so at the beginning, the indices where the thing that I'm looking for could be is index 0 all the way to size minus 1. right? In Racket, it's called vector length of v. They do also have vectors there. So yeah, here's binary search, calling binary search helper. You're looking for stuff, and it's always, well, split the search space in half and try and find things there. Okay, so if the search space is empty, you didn't find it. Like if start is past end for some reason, that means you're looking for something that doesn't exist. Otherwise, you look in the middle, right? You always find that midpoint of your search space. Where is that? So divide it by 2, and then go there in your vector or your list or whatever, and see how it compares to the thing you're looking for, right? If it's smaller, that means you need to search to the left, because that's where it could exist, right? So change the ending index. Otherwise, it's bigger than the thing that we're looking for, or the thing that we're looking for is bigger, and we need to look to the right. So change the start index so that we divide our search space in half each time we make a call. And otherwise, if it's not less than or equal to, we actually found the thing we're looking for. And usually in binary search, you want to give back the index of that thing you were looking for. Okay? And so here's like an example call for binary search. We'll be like, display line of binary search with vector of like, I don't know, let's say 1, 2, 3, 4, 5. And let's say we're looking for like 4 or something. I think that's the proper order. Yeah. And so that, in theory, should be okay. Let's try running this. Recursion.recit. Yay. And so you can see how it's calling things. It looks like it split it in half. It's looking in the middle, looking at 3, and it's like, no, it's not there. Let's look over here. And then it found 4 and 5. Apparently the middle of the sublist of 4 and 5, subvector, was 4 first, and so it found 4 the next time. And it's like, oh yeah, it's at index 3. Okay, so that's binary search. It's always look in the middle. If that's not what, if you found it, you're fine. Otherwise, depending on whether it's smaller or bigger, search the left or right half. And if you're looking for something that doesn't exist, your search space is empty, and you're done. Okay, so return some special like -1 value if what you're looking for wasn't actually in there. So if I was like looking for instead of that like -4, let's just delete it. If I was looking for -4, then it's like it couldn't have been there. Start and end kind of like passed each other. Couldn't find it. Okay, so that's binary search in a nutshell. There's also merge sort, which I hope you've also seen before. So I'll show you that one too. And yeah, let's think about it. Let's think about it too. So merge sort really is divide and conquer. All the textbooks agree on that one. What you do for merge sort, this is a sorting algorithm. What you do is you divide the array in half, which is going to take constant time to like make 2 halves, right? And then you're going to recursively sort each half. So like here is, let me show this to you. Here is like your array that you're trying to sort. Let's do it in reverse order, the worst order that it could be in. And then you like divide it in half, and here's what happens. Or actually, for reasons, let me make it 4, 2, 3, 1. That'll be prettier. So then you split it in half, and like you go and sort this subarray of 4, 2, just 4, 2. Then you sort this subarray of just 3, 1. So the recursion will make 2 and 4. The recursion will make 1 and 3, and then your job is to merge them all back into the pretty 1, 2, 3, 4. The final sorted list, because you have 2 sorted lists to work with. Okay? So yeah, you have to make those 2 smaller arrays. That's going to be n times, and work. And then you recursively sort each half. We don't know what that is, but it's going to take n over 2 time, right? Because it's a half small list. And we're doing that twice, because there's 2 halves. And we got to merge them back. And that involves iterating through each of them, essentially, and building up a bigger list, which is going to be, again, linear time. Okay? So this is merge sort. I don't want to go through too much of it, but that was essentially the idea, right? The base case is if you already have a size 1 or size 0 list that you're trying to sort, it's already sorted. Otherwise, you got to split it in half. So you have your left list and your right list, and then you recursively sort each of those, and then you merge them together, and merge is a different function that kind of does the heavy lifting of being like, okay, do I want to take from the left or the right now? and it just keeps going. Okay, so it is essentially iterating through though, and so it's going to be linear time. Definitely study the code if you're interested. And now I want to talk to you about how to solve like recurrences that, I mean, they have things, smaller versions of the same number inside of it. How are we going to cope with that? Okay. One way to do it is to use trees. So for factorial, at least, we can solve the recurrence not too badly. You remember the recurrence? It was the time that it takes to run factorial is the time that it takes to make the recursive call plus some constant work at each recursive call. And really, instead of +1, I should say plus like constant work. We can solve for this. Okay, we can totally solve for this. Here's what happens. And like at the base case too, right? The base case is immediately return 1, so that's constant work. With these together, we can pretty much solve for what it should be. So here is me calling factorial of like 5 or factorial of n or something like that. Okay, so here I am calling factorial of n. That I'm trying to figure out what t of n should be. Well, at its level, it's going to do constant work. It's going to check the size of things, or it's going to make a recursive call and then do some returning. This is the returning bit. And then we pass off the rest of the work to t of n minus 1. That's the recursive call. We need to figure out how long it takes. Okay? So again, it's going to, if it's in the recursive case at least, give back some number after multiplying it. That's constant work, plus however long it takes to do the recursive call, which is t of n minus 2, right? It's always getting smaller each time. And so we're kind of unwinding this, okay? And so this becomes like whatever it takes to get to t of n minus 3. Here's t of n minus 3. It's just a bunch of chains of recursive calls with constant work at each call, all the way down to like t of 2, which is constant work, plus a recursive call at t of 1, which is constant work at the recursive call, down to, yeah, you can either have it return when it's 1 or when it's 0. Let's do 0, because that's what we were talking about before. And so one more time, like it goes to t of 0. That's finally our base case, and that's definitely constant. So this is the tree of computation, constant work at each level. And how tall is it? It's n, like, it's n elements, right? N calls. It's n high. Height of this tree is n. Okay? And so it's n times constant work, which is n times constant work, which becomes constant, or not constant time, linear time. You see that? That's how you can figure out what a recurrence that you calculated actually is in terms of time complexity. Isn't that quite nice? All right, let's talk about binary search and about merge sort next. So what is the recurrence for binary search? So if you're trying to call binary search on a size n vector, it's going to do how much work? Well, it's got to make a recursive call, which essentially halves the subarray, halves the array, and tries to find it in that smaller by half array. And so here's the recursive calls amount of work that it's going to do, t of n over 2. Okay? Plus, based on that answer that it gives back, it needs to like return it and do things based on that. So it's again constant work. Okay? If you stare at the code long enough, you should see that. Here's it doing constant work after it's made the recursive call. It's just giving back that answer. Okay? Whatever it gives back. And to return something and like to compare things at each level, that's essentially constant time. Okay? So that's the recurrence for binary search. And also when it gets down to like the smallest thing, like an empty or size 1 subarray, let's call that t of 0. That's again defined to be constant work. Okay? So this is a different recurrence, and let me show you how to solve for it. So here is what's happening with that. T of n equals t of n over 2 plus constant work. So let's draw the tree for this. So t of n, what are we doing? How much work? At its level. And it's doing some comparisons and making recursive calls. So it's doing constant work at its level and then calling off to half the size subproblem. Okay, so it calculates t of n over 2 next. That's the that's the little recursive call that it makes inside of t of n. And so then we have constant work at its level, assuming it's another recursive case, and it's going to call off to half of this size to do the rest of the work, t of n over 4. You see how I'm like expanding this? That's the goal. That becomes theta of 1, again, constant work at that level, down to like n over 8, which is again constant work at that level. And it's going to keep on having until we get down to the last level, which is the base case, t of 0. Yeah? Dot, dot, dot. And so the question is, well, we're doing constant work at each level. How many levels? How many times can you divide a number by 2 and still have something left, right? One last time you like integer divide by 2 and you get 0. How does this work? It ends up being log base 2 of n. Okay, log base 2 of n levels in this tree. Okay, and so that makes it log base 2 of n times constant work, theta of log base 2 over n time. And so that's the time for binary search that we know and love. That's how you can discover it. Okay, that's that. And then finally we have merge sort. That's the more complicated one. What's the recurrence for its time complexity? Well, t of n is equal to, you have to do, outside of recursive calls, at every level, you have to do that merging, which takes linear time. Theta of n work. And you also need to recursively sort each half of your array. And so that is, each half of the array is size n over 2. You have to do that much work to sort it. And there's 2 of those halves, right? So that's the recurrence for merge sort. Let's see if we can use trees to discover how it's going to do. And then again at the smallest level, t of 0, that's equal to constant work because it's already sorted. An array of size 0 is already sorted, or 1. So t of n is equal to 2 times t of n over 2 plus theta of n this time. Okay, so it's a bit different from binary search. Will logarithms show up again? I don't know. Let's find out. So yeah, like at the first level, you have t of n, and it's going to do at its level that much work, linear work. And then it's going to make 2 recursive calls to do n over 2 stuff. Yeah? So this is going to be t of n over 2 happening twice. Oh, each doing, plug n over 2 into this, that gives us theta of n over 2 work at each call inside of it. And then it also makes its recursive calls to n over 4, right? Again, plug n over 2 in for this. That's what we're looking at. And so that's going to go to n over 4, making its recursive calls 2 for each, right? Which is going to do theta of n over 4, theta of n over 4 a bunch of times, theta of n over 4, and that's going to itself make recursive calls. You have 8 of them, and eventually it's going to get down to the base case. We're going to have a size 1 or size 0 subarray, and that gives us t of 0 down here at the bottom, which is doing constant work at each of those levels, right? Constant work, constant work, constant work. It's splitting up things, okay? That is the goal. So the question is, again, how tall is this? How tall is this recursion tree? It is repeatedly dividing in half. How many times can you do that? Log base 2 of n times and still have something left. So this is, again, height log base 2 of n. And how much work is being done at each level? This one's easy. It's just linear work. What about this one? Oh, that's linear work again. You see how that's theta of n if you add them together? This one too. Add them together, you still get theta of n. At every level, you end up getting theta of n. Really, this should be like t of 1 because everything goes down to a size 1 list, but that's okay. Again, it's theta of n at this level. So it is log base 2 of n high by theta of n work at each level. So that becomes theta of n log n. That is merge sort's time complexity. And that's how you can discover it. Isn't that cool? So this is kind of hand wavy, but this is a standard way of doing these things. Definitely take a look at how your book is talking about these trees, but this is one valid strategy. Okay? All right, so with that, I have just a few more things to talk about. The first thing that I want to do is have you give a recurrence relation to describe the time complexity of this minimum of a sequence algorithm. Here it is. And so, like, think about the time complexity of the base case, like when the length is 1, what's t of 1, and then what's t of n for some arbitrary n in the recursive case. Okay? What do we think? So definitely the time complexity for like this one is like constant work in the base case, right? You're just getting the first element and returning it back. That's all constant stuff. Then for the recursive case, you're making the recursive call on what size of thing? A one smaller list, right? You're making a single recursive call on a one smaller list. And then how much work are you doing in addition to that? You have an if statement that's returning stuff, just some simple comparisons. And so that is constant work outside of the recursive call. And so that would be the recurrence relation. We actually have solved this already. That's the same as factorial. And so it is a linear time algorithm. Hey. Which makes sense. You gotta visit everything to find the minimum. It's secretly doing linear work. Isn't that cool? So I had that, and then let's keep going. I want to keep giving you a bunch of these because recurrence relations are kind of tricky to wrap your mind around. I want to give you a bunch of examples to try. And then I have one nice way of solving every single recurrence relation that has a certain form. I'll teach you that too. So here's this one. Here is a find max algorithm. Instead of find min, it finds the max. Okay? It's a divide and conquer algorithm, actually. It doesn't work the same as our find min, or our min list, whatever we called it. So take a look at this code, kind of see how it's working, and see if you can give a recurrence relation for this one in terms of the number of operations that it's performing on an input list of n items. Again, it's trying to return the max. So if the size of the list is 1, it returns just that single element. Otherwise, it splits the list into 2. Crazy. Splits the list into 2. How dare it? And then it builds up the rest of these. So it finds the max of that one and the max of that one recursively. And so there'll be some smaller t's involved. And then it does some work at the end there to figure out which one to give back. Okay? And oops, I think I should be saying max here. Max 1, max 2. I think I changed this from find min to find max. So this is what it should have been. This is max 1 greater than max 2. Excuse me. Otherwise, return max 2. That seems to correctly return the max now, I hope. So with that in mind, come up with the recurrence relation for what it's doing. All right, so if we're in the base case, where there's just a size 1 list, what's the maximum immediately? It's just immediately one thing to do. Just return one thing, okay? Otherwise, if we do it this way, if we're in the recursive case, we have to do some constant work to figure out the ending index. Let's assume, just for the sake of example, that it's immediate for us to make these smaller lists. Like maybe you could use indices in like a helper function like I was doing in binary search. You don't have to build these actual lists if you don't want to, and that would save time. So let's assume that this is also constant time. It doesn't have to be the case, though. That could have been linear time. We're going to make 2 recursive calls to 2 lists that are half our original size. So 2 recursive calls to half the size. That is the first bit. And then the rest of the work, all this stuff, it looks to be constant to me. Okay? So let's assume that it's constant, and that is another potential algorithm. Okay? So that is find max. All right. Now, let me show you something. Let me show you something very, very nice. Instead of having to do these tree things, some very smart people have come up with ways of solving recurrence relations that don't require us to think at all. It's really, really nice. So here's something called the master theorem. If your recurrence looks like this in a very nice way, and it usually does, you can immediately solve the recurrence, okay? Many of them look like this. T of n is equal to some a times t of n over some b plus some n to the power of a constant d amount of work at each level, okay? So the master theorem lets us solve all the recurrences that look like this, right? And so it'll work for merge sort, where t of n is equal to 2 times t of n over 2 plus theta of n. And then it'll also work for binary search, where t of n is equal to t of n over 2, that recursive call, plus constant work at each level. Let's use that. Okay, so let's come up with the value. So a in here is 2. A is 2. B is 2. And D is 1. Right? And so let's use the master theorem now. So if A is less than B to the D, no, A is equal to B to the D, right? B to the D is 2 to the 1, which is 2. A is equal to that. So we have this case. That means t of n is, immediately we can conclude that it is theta of n to the d, which is just 1, times log of n. Nice. That was easy. Binary search, we had A being just 1, B is again 2, and D is 0, right? Because it's constant work. So what is that? Let's find out. So A then is less than B to the D. No, B to the D is equal to 1 again, right? 2 to the 0, anything to the 0 is 1. So again, A is equal to B to the D. So we're in this case once more, and so we have theta of n to the d, which is n to the 0, which is 1, and this is the only thing left, log of n. Theta of log of n. Isn't that beautiful? And you can also use it to solve this one. That is the idea, and so that's the master theorem. Very, very useful. Some very smart people at, I think, MIT came up with it. So let us thank them. All right, so your last exercise for today's lecture is use that master theorem, please, to solve for the asymptotic complexity using theta notation of each of these weird-looking recurrences. Making a bunch of weird-looking recursive calls. Who cares? You can solve them. Okay? So try them. And then we'll come back and talk about them. So here it looks like A is 2. Here A is also 2. Here A is 7. Here A is 7. Here B is 3, B is 3, B is 4, B is 4, and then D is n to the 1, so 1, 0, 2, and 1. I think that is correct. Yeah. So now we can just plug all that in. Is this true? Is it false? So B to the D is 3. A is smaller than it. So it looks like we're in this one for the first case. So we have theta of n to the D. Theta of n to the D, but D is 1, so theta of n. This is apparently linear time. Crazy. B to the D here is 1, which is less than A. So we're in this case. And so it's a weird looking one. It's theta of n to the log base B, so 3 log base 3 of A, which is 2. So that's a weird looking exponent, but it's an exponential algorithm. Crazy. So that's that. B to the D here is 8, which is bigger than A, so it looks like we're in this one. That is theta of n to the D. So this is n squared. It looks like this guy is winning out compared to this bunches of recursive calls. All right. And then finally, we have the last one. B to the D is 4. That is bigger than 7. So we're in this one again. And so that, oh, wait a second. B to the D, yeah, B to the D is 4, which is bigger than 7. Yeah, that is correct. That seems to be correct. And so we have no, I'm silly. Excuse me. I was so confused. B to the D is 4, which is this. It's smaller than 7. There we go. Thinking one thing and saying the other thing is never easy. So here we go. It's this rule. It is theta of n to the log base B, log base 4, cool, of A, log base 4 of 7. So it's another exponential algorithm with a weird looking exponent. But yeah, if you ever have a recurrence relation that has this form, and usually they do in programming, we have a solution immediately. Some people did all the math for us. You can go look up the real proofs if you'd like, but this is called the master theorem. Okay? And that is where I would like to leave you. So hopefully you're enjoying us finally talking about computer science stuff and really proving that like things are doing what they should do with induction combined with recursion. That is a beautiful, beautiful thing that we now know how to do. Okay? So that's one of my favorite things in this class to teach. So that concludes today's lecture. I don't think I have any new lab for you. That was given out last week. So I will just see you next week.